Okay, so for this equation, we're going to be deriving our energy balance equation for a flow problem. So what we want to start out with is our cylinder, which is our system. We have a mass coming into our system. Say it's from that side and coming out on this side. Okay, so we want to start out with our three forms of energy that we know are in our system, and these are all going to be multiplied by our mass of our system, since that's how we get it. So first we have our internal energy, which we're going to represent as our U, and then we want to add that to our potential energy, which we always have in a system, and our kinetic energy, because we have mass coming in and out, so it's going to be our velocity squared over 2. And this will all be for our system. And we also want to add this D, since it's a differential mass coming in and out of the system. So now we want to break this energy equation into its different parts. We have first our mass coming in, which will be the same, internal plus potential plus kinetic. For that times our differential mass coming in. And then that will be subtracted by our mass coming out, since this is a difference in our energy coming in and out. So we have the same thing, internal plus potential plus kinetic, and that will be times our differential mass coming out. Now we want to account for a couple different types of energy that we also have in a system, or we potentially have in a system. Sometimes we won't have these, but first we will put our dq, which is accounting for if there's a stir. I didn't draw anything in here, but if the fluid is getting stirred inside the system, that will add an energy to our balance equation, and then our net work force. So now we want to account for our injection force. Our injection force is going to be our work, which is just our force times distance. Our distance we can break up, and that will just be our velocity over our density. And now we can break up this velocity right here, which is going to be our mass over our area. So that will end up being our mass over density times area, and then we can multiply our force, but our force is going to be just our usual pressure times area. Then we see our pressure, our areas cancel out, and we're just left with the pressure over the density times our differential mass. So we want to add this to our energy balance equation, and we know that there's going to be two different sets of pressure and density, since obviously we have a mass coming in and a mass leaving. So it'll be the same thing, pressure over our density times our differential mass coming in, subtracted by, since it's the difference, our pressure over our density times our mass going out of the system. So that is what we're left with for our energy balance equation for a flow problem. Okay, so for this equation, or for this problem, we're going to want to take our energy flow equation, and we want to derive Bernoulli's equation from it. And for those of you that don't know what Bernoulli's equation is, it's basically a simplified version of what we already have in our energy balance equation for a flow problem, except we're assuming steady state and no non-flow work and no stir, which dq. So basically we want to isolate these variables on one side. And another thing that we know is that all of our masses, so our dm, equals our dm in, which equals our dm out. So that simplifies this problem a lot more as well. So what we want to start out with is this whole energy balance part that it's equal to right over here is all going to be set equal to 0 for the Bernoulli's equation. So now what we're left with, I'm going to group all these terms since we know that these masses are going to be just dm. I'm going to just associate them as dm since we know that they're all equal to each other. Now we can basically merge these two equations together. So it will be our u1 minus our u2 plus our gravity times our h1 minus h2. And that will be times, or plus our v1 squared minus our v2 squared over 2. And now we can, as I said, we can just keep that as dm since we know all the masses are equal to each other. So then what we add on is our, what we have is, sorry, I'm running out of room, our dq, so our stir if we have one, our non-flow work. And let me put the camera in frame. And then also we have our pressure differences. So it will be our pressure over our density times dm minus, pressure 1 minus pressure 2 over density minus dm minus dm. So this will also be able to be merged. I'm actually going to do that right now. So it will just be P1 minus P2 over our density times our differential mass. And so like I said, all of these terms are going to be 0. But first I want to take all the other terms, which will be our height, or our potential energy, kinetic energy, and our pressures. I'm going to put them all on this side of the equation. So what we're left with is our, it'll be our P2 minus our P1. So that will just be equal to our differential pressure, or our delta P, which is our difference in pressure, over our density times, then we're going to add that to our gravity times, which is our potential energy, but this H2 will be H2 minus H1 instead of H1 minus H2 since I'm moving it to the other side. So that can just be our delta H. And then added to that, I want to keep these terms are going to switch obviously again. So it will be my difference in velocities, but these are squared, so I'm just going to keep them like this, over 2. And that will all, I think that's all we have. So yes, we will take that over to the other side, which will be equal to our u1 minus u2 and plus dm. Well, this is actually all going to be multiplied by dm still, this is. And plus our stir and dw, our non-flow work. And that will all be divided by our dm since that will be moving over from this side of the equation. But when we get to Bernoulli's equation, we want all these terms right here to equal 0. So this whole right side of the equation is just going to be equal to 0. And what we're left with is our delta P over our density plus our gravity times our difference in our height, that is not divided by anything, plus V2 squared minus V1 squared over 2. So now we have our simplified version of our energy balance equation when we have some set parameters, which gives us the Bernoulli's equation. Okay, so for this next problem, we want to find the change in temperature of our pipe for a pressure drop of 60 psi in a pipe that has no heat flow, a constant diameter from the inlet to the outlet, and no change in height from the inlet to the outlet. So what we have is we start out with 60 psi, and it drops to 0 psi like that. And so first we want to lay out our energy balance equation. So what we have is our pressure drop, 0 minus 60 which is in PSI. And since this is our energy balance equation, we want to have the density on the bottom, which was for water in this case. So our pipe is going to be filled with water. So that's 1,000 kilograms per meter cubed. And then we want to convert this PSI to pascals. So 101.315 for 14.7 PSI. And then all that will be equal to the negative heat capacity of water in this case, since we have water in our pipe, and that will be multiplied by our temperature drop, which is just going to be, I could just change this. This is just going to be our change in temperature, which we are trying to solve for. So what we have is our CV, that's all we need to plug into, which is 4185, what is it? Negative 4185 joules per kilogram Kelvin times our change in temperature. And then all we have to do is solve for our temperature change, and I have this on my calculator over here, which we got to be 0.1 Kelvin. So that will be our change in temperature with a pressure drop of 60 psi to 0 psi. Okay, so for this next problem, we're going to be taking a tank or some type of container and trying to find the flow rate at the bottom of the container if there was a hole punched in it at the very bottom. So we have a hole, and then our fluid is obviously emptying out of that hole. So we want to use Bernoulli's equation to find our end flow rate, and the way we want to do that is we're really just looking for our velocity at the end, since we know our flow rate is just going to be equal to our velocity times our area. So what we want to do is we want to look at this problem and start identifying some of the variables that we have. So at the top, we can just say that is our start, which is our 1, and at the bottom it'll be our 2. So we have, at the top, we have some height. So that height is just going to be the height of our container, and the bottom is what we're going to call as 0, since that just makes the most sense where to start 0 from. So our height 2 at the bottom is just going to be at 0, and if we look at this, we can just see that that difference is just going to be that height right there, which is just the height. So now we also want to look at is we have a velocity at the top and a velocity at the bottom. Velocity at the bottom, obviously there's some velocity of this water exiting the container, which is currently unknown right now. We can't really figure that out unless we use Bernoulli's equation, and that's really what we're solving for. But at the top, we know technically there would be some velocity coming down, but we're going to assume that this container is so big that this velocity of the water level lowering is negligible, so that will be 0. So we have our velocity at the top is 0, and velocity at the bottom we do not know. Now we want to look at our pressure, since that's the next thing in our Bernoulli's equation. We have a pressure at the top, which our pressure at the top we know is going to also be 0, since this fluid at the top is not, there's no pressure at the top of the container. And then at the bottom we see that this the water exiting is not spreading out. There's no pressure felt on the outside, or else that water would just be spewing out in all different directions. So we know the pressure at the bottom also is going to be 0. So now we can set up our Bernoulli's equation. We know that that is going to be our change in our pressure, P2 minus P1 over our density, and that will be added to our potential energy, which is our gravity times our difference in our heights, and that will also be added to our velocities, which is our kinetic energy. And for Bernoulli's equation, we assume that the right side of the equation is 0, so we don't have some of these factors like internal energy and net work force and other things like that. So now we can start plugging in a couple of these values that we already have. So first we have these two pressures. So the pressure at the top, we already said that that's 0, and the pressure at the bottom, we know that's also 0. So this whole part of the equation, our pressure, is negligible in this case. So then what else do we have? We have a height over here, which our height too we know is going to be 0, since we took that bottom of the container to say that that was the point of 0 height. And then at the top, we know that that is going to be just h, since we signified that our h value is the height of our fluid in the container. So what we have is, we can see that this is going to be a negative g times h, and then we want to add that to our velocities. Once again, I said that our velocity at the top, we knew that was also 0, so we can take that out, and conveniently we're left with just our v squared over 2, which will help us solve this equation, since we need to find v2 for our flow rate. So what we do is take everything to the other side, multiply it by 2, so it's going to be 2gh, and then take our square root, or squared out and with square root. So we're left with our v2 to equal 2 times the gravity times the height. And now we basically have solved for our flow rate. All we have left is our, we have the flow rate to be equal to our velocity times our area. So we already have a velocity here, and that will just be 2 times gravity times height, and that will be multiplied by our area. So in the problem, we didn't specify what the area of our hole is, but obviously we'd try to plug in our area there. But that's really what we're just left with, is our flow rate is equal to square root of 2 times acceleration due to gravity times our height of our fluid in the container times the area of the hole that this fluid is exiting at.